Assalamualaikum to the panels. My name is Mohd Adam bin Mohd Razmi, and today I will be presenting my research proposal titled Sex-Based Differences in the Abduction Angle During Drop Vertical Jump Among UiTM Recreational Athletes. Let us begin with background of the study. Over the years, analyzing lower limb mechanics has become essential in sport biomechanics, not just for performance, but for preventing severe injuries like ACL tears. To do this, we often use the drop vertical jump or DVJ as a standard assessment tool. As noted by Bates in 2013, improper landing techniques, especially those involving abnormal knee motion, are heavily linked to an increased risk of injury. This is particularly relevant for recreational athletes who frequently perform these jumps but may lack the refined techniques of elite players. The specific variable we are looking at is the knee abduction angle. This measures the displacement of the knee during landing and serves as critical indicator of joint stability. Research by UNO 2020 highlights that a larger knee abduction angle is directly associated with higher knee valgus motion, which is primary mechanism for non-contact ACL injuries. By understanding this angle, we can identify how athletes absorb force where their mechanical imbalance lie. We cannot ignore the significant role of sex-based differences. Literature consistently reports that female athletes exhibit greater knee valgus angles and moments than their male counterparts, as seen in studies by Ford 2010 and Carson and Ford 2011. These differences aren't random. They are driven by distinct anatomical factors, muscle strength imbalances, such as rotational strength in the knee and variation in neuromuscular control, which Kiriyama in 2009 suggests lead to the distinct movement patterns we see between sexes. Moving on to the problem statement, injury prevention is a major concern in sport biomechanics, particularly for athletes involved in jumping sports. Literature by Hayward 2009 and Crostorm 2016 has identified that improper alignment, specifically excessive knee abrasion or valgus motion, is a significant predictor for ACL tears. Research by Bates 2013 further shows that poor landing mechanics lead to increased stress on the knee joint. Unfortunately, while professional athletes receive correction for this, many of our recreational athletes continue to demonstrate poor mechanics simply because they lack access to biomechanical screening. This issue is compounded by sex-based differences. Studies by Ford 2010 and Kuriyama 2009 indicate that female athletes are more susceptible to these injuries due to differences in muscular strength, hormonal factors, and anatomy. However, most of this data comes from elite population. There is a clear gap in the research regarding recreational athletes, which is why it is critical to investigate how these differences manifest in every university athlete. This study is guided by three specific research questions and corresponding objectives to ensure a comprehensive analysis. First, I aim to establish a baseline for our male participants. Therefore, my first objective is to determine the knee abduction angle specifically for male UiTM recreational athletes during the drop vertical jump. This directly answers the question of what the landing mechanics look like for the specific group. Second, I will apply the same analysis to the other group. My second objective is to identify the knee abduction angle for female UiTM recreational athletes, allowing us to capture the specific biomechanical data for women in this population. Finally, the core of this study lies in the comparison. My third objective is to examine the sex-based differences in these angles. This allows us to statistically analyze the variation in landing mechanics between males and females to see if the significant biomechanical disparities exist, specifically on knee abduction angle. To statistically test our research problem, we have established two opposing hypotheses. First, our attentive hypothesis predict that there is significant difference between sexes in knee abduction angle during drop vertical jump among UiTM recreational athletes. This hypothesis aligns with previous global literature suggesting that males and females land differently due to anatomical and neuromuscular variation. Conversely, Our null hypothesis act as our baseline. It states that there is no significant difference between the sexes in knee abrasion angles within the specific population. Through our data analysis, we aim to determine whether there is enough evidence to reject this null hypothesis in favor of alternative. The purpose of this study is to compare off-knee abduction angle during drop vertical jump between male and female among UiTM recreational athletes. This study holds significant value in three key areas. First, regarding injury risk identification. By understanding the variation in knee ablation angles, we can better identify the specific biomechanical factors that lead to lower limb injuries, particularly those related to ACL. This addresses the root cause of improper landing mechanics. Second, for coaches and trainers, these findings provide a crucial reference. It allows for development of gender-specific training programs. This is especially important for recreational athletes who engage in high-demand activities but rarely have access to professional biomechanical assessment to correct their techniques. Finally, from sport science perspectives, this research contributes to localized data. Rather than relying on solely on general studies, we are providing a baseline specifically for UiTM recreational athletes. This supports future research on strength imbalances and aligns with the national goal of promoting safer sport participation at the recreational level. Every study has its boundaries and constraints. For our delimitations, which are the choices we made to narrow the study, we are focusing exclusively on UiTM recreational athletes who are trained at least 120 minutes per week. We are intentionally excluding the elite or varsity players to keep the data specific to the recreational population. Furthermore, our scope is limited strictly to the knee abduction angle during drop vertical jump rather than analyzing the entire lower limb kinetic plan. Regarding limitation, which are potentially weaknesses, we acknowledge that our sample size is limited to one university. This means our findings may not be fully generalizable to athletes to other institutions. Additionally, while we are using advanced 3D motion capture, we must account for technical challenges such as potential errors in marker placement or skin movement artifacts which can slightly influence the measurement accuracy. To ensure the validity of our findings, this study relies on four key assumptions. First, we assume that all UiTM recreational athletes will perform the drop vertical jump with maximum effort and maintain consistent landing techniques throughout every trial. Second, we assume that participants will be honest about their training history and will fully comply with all safety instruction and testing procedure during the sessions. Third, we rely on the technical assumption that our 3D motion capture system is correctly calibrated and will provide accurate, reliable recordings of knee abduction angles for both groups. Finally, and perhaps most importantly, we assume that any differences we observe between males and females are due to genuine sex-based biomechanical variations rather than being the result of random measurement errors or inconsistent performance by the athlete. To ensure we are on the same page, I will define the key operational terms used in this study. First, sex-based differences refer to the specific biomechanical variation we observe between males and females due to anatomy and muscle control. Our primary variables is the knee abduction angle, KAA. This is the inward or valgus movement of the knee during landing. A higher angle is critical because it is often linked to the higher risk of knee injury. We measure this using the drop vertical jump (DVJ) as a standard dynamic task used to evaluate landing biomechanics. Our sample consists of UiTM, recreational athletes, defined specifically as students who train at least 120 minutes per week but do not compete at the elite varsity level. Finally, this research is centered around protecting the anterior cruciate ligament (ACL), which is the knee's major stabilizer against rotational forces. To understand the injury mechanism we discussed in the introduction, we must look at the anatomy of the structure wrist, the ACL. As you seen in the diagram, the ACL is located deep within the knee joint, connecting to the femur to the tibia. Its primary role is to act as a mechanical stabilizer, it prevents the shin bone from sliding too far forward and helps control rotational movement of the knee. However, as mentioned in our introduction notes, this ligament is not invisible. It is specifically vulnerable to the biomechanical forces we are studying, particularly knee abduction or valgus thrust. When an athlete lands with poor alignment, it displaces excessive strain on this specific ligament, which can lead to rupture. Understanding this anatomical vulnerability explains why we are so focused on analyzing landing mechanics and sex-based differences in this study. I've selected four key studies that directly related to my variables. First, Bates 2013 established a critical link between landing mechanics and injury risk. They utilized 3D motion analysis to confirm that excessive knee adduction or valgus motion is a major risk factor for SCL injuries because it significantly increases stress on the knee joint. Next, Ford 2010 focused specifically on sex-based differences. Their longitudinal study found that female athletes consistently exhibit greater knee valgus angles and reduced knee flexion compared to males. This helps explain why female athletes are statistically more prone to knee injuries. Moving to the underlying mechanism, Kiriyama 2009 investigated why these differences occur. They found that males possess higher rotational muscle strength, which give them better control over shank rotation. In contrast, the females often demonstrate weaker rotational strength, leading to greater internal rotation and higher abduction angles. Finally, Ueno 2020 highlighted the importance of the hip muscles. They found that reduced force in the gluteus medius combined with high ground reaction forces strongly predicts dangerous knee abduction moments in female athletes. Collectively, this study confirmed that sex, muscle strength, and landing mechanics are deeply interconnected, justifying the need to examine these specific variables in our recreational athlete population. In this chapter, I outline the complete framework used to conduct this study. I will describe the research design, how the population was sampled, and the specific instrumentation used for data collection. Crucially, this section details the standardized protocol for DVJ to ensure consistency. The primary objective of this rigorous methodology is to guarantee that our measurement of the knee abduction angle is both valid and reliable. This allows me to accurately compare the biomechanical differences between male and female UiTM recreational athletes. For the research design, this study utilizes quantitative and non-experimental causes comparative design. I chose this approach because my primary goal is to measure and compare a specific biomechanical variable between two distinct independent groups, which is males and females, at a single point in time rather than conducting a long-term intervention. In terms of variables, our independent variable is sexes, comparing males versus females. Our independent variable is the knee abduction angle, KA, specifically recorded during the landing phase of drop vertical jump. For sampling method, I utilize a purposive sampling technique. This ensures that I specifically recruit athletes who meet my definition of recreational, those training 120 minutes per week but not competing at the elite level. To determine the appropriate sample size, I conducted an priori power analysis using G-Power software. I configured this for an independent sample t-test to ensure I could detect meaningful biomechanical differences between males and females. I used input parameters based on the foundational study by Ford 2010, which indicated a large effect size of 1.1, setting our significance level at 0.05 and statistical power at zero point 0.8. The analysis calculated a minimum requirement of 28 participants. However, to account for potentially data loss or technical errors during motion capture, I have added a 20% buffer targeting a final sample size of 34 participants, which 17 males and 17 female. To ensure the accuracy and reliability of my data, I using the three specific categories of instrumentation. First, I utilize standard anthropometric tools. I use a medical grade steniometer and digital scale to calculate BMI, which serve as a control variable for my inclusion criteria. I also measure leg length to standardize the kinematic data during analysis. Second, for the core of my data collection, I use high resolution 3D motion capture system. This setup consists of 10 infrared focus cameras synchronized at 250 Hz. I attach specific retro reflective markers to specific anatomical landmarks from the pelvis down to the toe. This allows me to accurately reconstruct the participant's lower limb model and calculate the knee abduction angle in the frontal plane. Finally, to standardize the task, I use a custom built drop jump box. I selected a fixed height of 30 centimeter based on the standard set by Ford 2007 for assessing ACL injury risk. This ensures that the potential energy and impact forces are consistent for every athlete, guaranteeing that any difference we see are due to biomechanics, not the equipment. This flowchart summarizes the 7 key steps of my data collection process. First, the ethical approval. The study will officially begin only after receiving approval from the UiTM Research Ethics Committee. Second, participant requirement recruitment. Once I approve, I will recruit recreational athletes through digital poster and social media. Third, PARQ. Interested candidates will be screened using the physical activity readiness questionnaire to ensure they are safe to participate. For briefing, eligible participants will then receive the full briefing on the testing procedure and sign the informed consent forms. Fifth, drop vertical jump. This is the core testing phase. Participant will perform the drop vertical jump task from a 30 centimeter box while their movement is recorded by the motion 3 motion capture system. Six, data analysis. The raw motion data will be then processed, labeled, and filtered for analysis. Last, comparison. Finally, I will compare the knee abduction angle between males and females, specifically analyzing the difference at two critical moments, initial contact and peak knee flexion. For the data analysis phase, I will begin with descriptive statistic, calculating the mean and standard deviation to summarize the demographic characteristic of my participants. To address my research question, I have defined my variables. Our dependent variables is sexes and our independent variable is the knee abduction angle during drop vertical jump. This leads to our hypothesis. Attentive hypothesis predicts that there is a significant difference between males and females, while null hypothesis assume there is no significant difference in knee angles between the groups. To test this, I will utilize the independent sample t-test, which is the appropriate inferential statistic for comparing the means of two distinct groups.